This is problem 25 from electric force. Find the electric force on each of the atoms in the sodium chloride crystal. The interatomic separation is 2.82 times 10 to the negative 10th meters. So that means this distance here, which we'll call 2a, so that's 2 blocks, is 2.82 times 10 to the negative 10th meters. On the graphic above, sketch the direction of the electric force on each charge. Well, I have a negative charge here, and these two are positive, so that negative charge is going to be attracted to the positive charges, but away from this negative charge. But this charge is farther away, so overall, when you add those forces together, you're going to get a net force pointing inward. And by symmetry, that would be the same for all four charges. We're going to go through this problem a little bit quicker. How should the electric force on the upper right sodium ion compare to the electric force on the lower left sodium ion? Upper right, lower left, those are equal in magnitude and opposite in direction. Same magnitude, opposite direction. And because all of the charges, the absolute value of the charge is E, by symmetry we can say all these forces have the same magnitude. Therefore, I'm just going to calculate the force for one charge, and then we can write down what the force is on the other three charges. So I'm going to call this charge 1, this charge 2, this charge 3, and this will be charge 4, and I'm going to find the force on charge 4. So when I do that, this will be my point of interest, and I want to find the field from the other three charges. So I'm going to call this E1, E2, and E3, and that's the field at this point from charge 1, the field at this point from charge 2, and the field at this point from charge 3. Remember that the electric field is equal to kq over r squared in the r hat direction. For charge 1, r hat is pointing this way, that's negative I hat. So this will be negative I hat. Kq is equal to E because that's a positive ion. And the distance between these two charges is 2 blocks, which is 2a squared. You could also just say A is equal to 2.82 times 10 to the negative 10th meters, but because we used 1.41 times 10 to the negative 10th meters for A in lab, we'll continue to do that now. Okay, and then we have charge 3 here, and going from 3 to 1 gives us the direction of r hat. So from the charge to the point of interest, that's pointing in the j hat direction, and this is k times the charge, which is E, divided by 2a squared. And then, this one's a little more difficult. Let's see. So, for this one, I'm going to write out my r vector, and going from the charge to the point of interest, that's 2 blocks to the left, which is minus 2a I hat, and then 2 blocks up, so that's plus 2a j hat, and then I have k times this charge, which is negative E, so kq divided by r squared would be 2a squared plus 2a squared. And then when we multiply this by r hat, this becomes to the 3 halves, and this, I'm just going to stick it in the numerator here because I'm tight on space. Okay, and remember that all that comes from E is equal to kq over rx squared plus ry squared to the 3 halves times rxi hat plus ryj hat. Rx is equal to negative 2a, ry is equal to 2a, and it doesn't matter if it's negative when you're squaring it. So then let's simplify this a little bit. So I have the negative sign here. If I multiply this negative times the I hat component here, that gives me something positive. So the I hat component is positive, the j hat component is negative. So, and let's pull out the 2a and we'll call this 2kea times I hat becomes positive, j hat becomes negative, divided by 2a squared, that's 4a squared, plus, oops, this 2 was supposed to be outside of the parentheses. So that's 4a squared plus 4a squared, which is 8a squared to the 3 halves. And then a squared to the 3 halves is just a cubed, but I have an a in the numerator here. So a divided by a squared to the 3 halves leaves me with an a squared in the denominator. This is I hat minus j hat. And then let's 2 divided by 8 to the 3 halves is equal to 1 over 8 times the square root of 2. And you can just take my word for that, or you can check to make sure that that's true. And I'm going to leave E2 like that. And then remember that the force is equal to the charge times the net field. So our charge is charge 4, which is negative E. And this is the net electric field, so this is E1 plus E2 plus E3. Oops. Negative E times E1 is negative KE over, let's call that 4a squared in the I hat direction. E2 is plus KE over 8a squared times the square root of 2, I hat minus j hat, and E3 is KE over 4a squared in the j hat direction. So we multiply everything by negative e, and then we're going to group the I hat terms together and the j hat terms together. So I have negative e times negative ke, so that's ke squared over 4a squared in the I hat direction. And then from this term, I get a negative ke squared over 8a squared over square root of 2. So I can pull this outside, put the I hat at the end. This was my first term, so I just get a 1 there. And then for the other I hat term, if I pull out a 4 from the denominator, I'd be left with, pulling 4 out of 8 would leave me with a 2, and then I still have the square root of 2, and because of this negative sign here, that is negative. And for the j hat, this is ke squared, when I multiply by the e here, over 4a squared, but it's going to be negative. So let's pull this outside of everything. And then for the j hat, this term here will be negative 1, and then from this term here, if I have a negative times a negative, that makes it a positive, so that'll be plus, and then it will be this. You can check that on your own. Okay, and then we just have to put in numbers, and you can do that on your own as well. K is 9 times 10 to the 9th newtons times meter squared per coulomb squared. E is 1.602 times 10 to the negative 19th. We're squaring that. And A is half of 2.82 times 10 to the negative 10th. And we should get for this is the force on charge 4. And this is 1.88 times 10 to the negative 9th newtons, and this is I hat minus j hat, which is pointing in the correct direction for charge 4. Then we'll box this, and we'll say by symmetry, the force on charge 1 has the same magnitude, but this would be in the negative I hat, negative j hat direction. So this is 1.88 times 10 to the negative 9th newtons in the minus I hat minus j hat direction. And we can write the other ones down as well. Force 2 is 1.88 times 10 to the negative 9th. Oops, need my newtons in there. Force 2, this is charge 2, so force 2 is pointing this way. That's positive I hat, no, negative I hat, positive j hat. And then force 3 is pointing this way, so that's plus I hat plus j hat. 1.88 times 10 to the negative 9th I hat plus j hat. All right. So you can fill in any missing steps if necessary. That concludes problem 25.